Alright, so this video goes right along with the Bohr model packet, so have that out and ready to go. On the first page, look at the two models at the bottom. What do you notice is the difference between the two? Take time right now to write down the main difference between the two. If you wrote down something about the fact that the Bohr model has the electrons organized onto energy levels and that the Rutherford diagram just has electrons scattered randomly, you're exactly right. Bohr was the first scientist to say that electrons existed on specific energy levels, not just randomly wherever they felt like. The good science word for that is quantized or quantization. Record this definition at the bottom of the first page. There's not a space for it, just write it down. Energy can only exist at certain energy levels or have specific values. For instance, electrons can be on the first energy level or the second energy level, but they can't exist between the energy levels. Okay, flip the page over. The next thing you see is the definition for the atomic emission spectra. An atomic emission spectra looks like this. It's a pattern of colored lines, basically. When you take a mass of a specific element, in this case strontium, and you superheat it, meaning you just put a whole lot of energy into it, it produces specific colors of visible light that when you shine that light through a prism, it ends up looking like this. Think about all the Bohr models you've drawn for different elements. None of them are exactly the same because none of them have exactly the same amount of electrons, right? Because of this, they all produce different atomic spectra. Because this is true, we can use atomic spectra to determine what elements are in a specific mixture. So if you have a mixture, you're not sure what it is, you can superheat it, send that light that's produced through a prism, and it'll show you these different colored bands. This is also how we can determine what stars are made of, even though we've never actually visited a star. So look at all of these spectra for different elements. Notice how none of them are completely the same. Look at the four mixtures, A, B, C, and D, off to the right. Use the spectra for each of those individual elements to decide what elements are in each mixture. For example, look at mixture A, and you'll see there's a purple, a dark blue, a light green, and two yellows. So if you look over, those two yellows are definitely from sodium, and those other lines come from manganese. So for unknown A, that's manganese and sodium. So go ahead and record that for unknown A, and then finish the rest of these for B, C, and D. Tell what each one is on your paper. Alright, flip over to the next page. There are four separate hydrogen atoms there. We know that hydrogen only has one electron and that it sits on that first energy level. However, when hydrogen is superheated or when you put a lot of energy into it, that one electron gets too much energy to stay on that first level, so it likes to jump to higher energy levels. So for this segment, I'm literally just telling you what the electron does with different amounts of energy. This isn't something that you'll need to see like as a test question or anything. You just need to understand the process that I'm explaining to you. So for the first hydrogen atom that you see there on the left, the electron starts at energy level 1. We know that's where it naturally belongs. It fills the first energy first. When it absorbs energy from being superheated, the electron jumps up to energy level 3. So go ahead and fill that in on your sheet. Eventually, it doesn't like being at such a high energy level, so it falls back to energy level 2. However, when it does that, it has to get rid of some extra energy, so it releases that energy in the form of visible light. Specifically for this scenario where it jumps from the third energy level back to the second energy level, the visible light that it's going to give off or emit is going to be red. So fill that in on your sheet and also draw a little arrow. I tried to do this at the top of the picture, but I didn't do a great job. Draw a little arrow that shows the electron jumping from level 1 to level 3. And then if you want to, you can draw a little arrow showing it jumping back down to 2. And remember that when it jumps back down, it's releasing energy in the form of visible light. For the second hydrogen atom, the electron is still starting on energy level 1. We know that it belongs there. When it absorbs a certain amount of energy that's different from that first scenario that we did, when it absorbs more energy, the electron is going to jump up to energy level 4. So go ahead and draw that picture of it jumping from 1 to 4. Eventually, it doesn't want to be up there anymore. It doesn't like being at a high energy state, so it's going to fall back to energy level 2. When it does that, it's going to release energy again, and just like the one before, it's going to release it in the form of visible light. However, instead of being red light this time, it's going to be green light this time. So go ahead and get that down on your packet. For the third hydrogen atom, the electron starts on energy level 1. It's always starting there. That's its ground state. However, when it absorbs energy from being superheated, if it absorbs even more energy than it did for the last scenario, the energy level, instead of jumping up to level 4, will actually have enough energy to jump all the way up to energy level 5. Here again, it's going to get tired of being at a high energy state. It doesn't want to be excited, so it's going to return back to level 2. When it does that, though, remember, it's got to get rid of that extra energy. And so the way that it's going to do that, it's going to release visible light. Specifically for this one, that colored light, instead of being red or green, this time the light is going to be blue. For the last hydrogen atom, the electron starts on energy level 1 here again. When it absorbs energy, the most amount of energy that it can absorb, it's going to jump all the way to energy level 6. However, here again, it doesn't like to be at a high energy level, so it's going to fall back down to a lower energy level. In order to go to that lower energy level, it has to release the extra energy. It's going to release that extra energy as visible light, and for this last scenario with the most energy, meaning it's jumping from the 6th all the way back down to the 2nd. It's got to release the most energy. It's going to release violet or purple light. So depending on the amount of energy the electron in a hydrogen atom receives, so if it receives a little bit, or it receives somewhere in the middle, or it receives a whole lot of energy from being superheated, it can jump to energy level 3, 4, 5, or 6. When it falls back down and releases visible light, that light will either be red, green, blue, or violet. It's not going to be any other color. It has a very narrow range. So look again at this atomic emission spectrum for hydrogen. You should notice that the colored lines are the exact colors we just talked about. An atomic spectrum is produced by electrons absorbing energy, just like we talked about. So they're at a low state, a low energy state. They're absorbing energy from being superheated. They're jumping up to higher energy levels. Eventually, they get tired of being up there. They don't like being at high energy, so they return to lower energy levels. When they return to lower energy levels, they release that extra energy as visible light, and that's what we're actually able to see. So that's the cause of a emission spectra. So on the next page, the question reads, what do you think is the origin of the 4 colored lines in the atomic emission spectrum of hydrogen? So basically, why are those 4 colored lines there? Where do they come from? You need to write something along the lines of hydrogen atoms are superheated, the electron absorbs energy, and it jumps up, or it is promoted to higher energy levels, either 3, 4, 5, or 6, depending on the amount of energy. Eventually, it jumps back down, it returns to a lower energy state or a lower energy level. When it does that, it releases or gets rid of the extra energy as visible light, and that's what shows up as the colors we see on the atomic spectrum. That's what causes those little bands of light to be there. Moving on to the nature of light, look at this card describing red light. Find the symbol for wavelength. It's a Greek letter. It kind of looks like an upside down Y. Look at the illustration for wavelength and record it on your paper. Wavelength is basically the distance between the top of 2 neighboring waves. So you're measuring from the top of a wave to the top of the next wave. Basically, if they're beside each other and you measure from either top to top or bottom to bottom, you'll get the wavelength. Flip your paper over now and look at the symbol for frequency. As you can see from this card, it's a lowercase f. In the next box, go ahead and write this down for frequency. Essentially, frequency, as you can see from the picture, is how tightly packed the waves are. So if waves are high frequency, they're very close together, there's a lot of them that can pass like a specific point in a small amount of time. If waves are low frequency, it means they're really spaced out and only a few of them can pass in a certain amount of time. So when you think about frequency, think about how tightly packed together the waves are. Now look at all these cards in a row. On your paper, it asks you what happens to the wavelength and then the frequency as you move from red light to violet light. So look at the wavelength as you're going from red to violet and look at the frequency as you're going from red to violet, and go ahead and answer both of those questions now. If you observe that the wavelength decreases, meaning Red is really large, violet is really small for wavelength. You're exactly right. And also, the frequency increases. Red has a low frequency because the waves are pretty spaced out. Purple has a pretty high frequency. The waves are packed together. Basically, the red light waves are bigger, so they can't be as tightly packed. The violet waves are much smaller, so they can pack together more. Flip over. The next question asks about the relationship between wavelength and frequency. Like you said on the last page, if one goes up, so if wavelength goes up, the other one goes down, frequency goes down. That's an inverse relationship or an indirect relationship. Record this in the box that's written down. Inverse means a large wavelength means a low frequency. Small wavelength equals a high frequency. Looking back at these cards again, notice that the symbol for energy is just a capital E. The next question on your packet asks about what happens to the amount of energy as you move from red light to violet light. So look at those numbers for energy, record what you notice is happening to the energy as you move from red to violet. If you observe that the energy increases going from red to violet light, you're completely correct. The higher the frequency or the more tightly packed the waves are, the more energy they have. So violet has really small waves so they can closely pack together really tight, so they have really high energy. Whereas red has bigger waves, they're not as tightly packed, they have lower energy. Also, notice that the symbol for the speed of light is a lowercase c. I know that doesn't make much sense, but it is. Also notice that the speed of light does not change. For every single color of light, it is always a constant 3 times 10 to the 8th meters per second. No matter what color of light, the speed of light is always going to be the same or be a constant. All right, stick with me. We're almost there. The next thing is just a definition that you need to understand. So light can act like a wave or a particle, and a particle of light is called a photon. So if you ever hear photon, it's just talking about light. We as scientists just choose how we want to treat light for what we're currently working on. So when we talk about light, like wavelength and frequency, we're talking about it as a wave. But when we want to talk about things like photosynthesis and how plants receive light, it's easier for us to talk about it as a particle. So we talk about photons instead of waves. We just completely forget about whichever part we don't want to pay attention to. All right, now it's time for some math. Woo! This math looks really intimidating because of the scientific notation, but it's just basic multiplication and division, nothing stressful. So the first formula we're going to work with is right here for you. It's the speed of light is equal to the wavelength times the frequency. Basically, if a problem gives you the wavelength and asks for the frequency, or gives you the frequency and asks for the wavelength, this is the formula you're going to use. Look at the example problem. It's really self-explanatory. All you're doing is dividing that speed of light, which is c, by the frequency, which is f, to find the wavelength by itself, which is wavelength is that weird upside down y. So this is just worked out for you to give you an example of what's going on. All right, now it's your turn. The only thing important that you need to know is that when you're typing anything with scientific notation into your calculator, you have to use parentheses. So you're going to type in open parentheses and then type in the number in scientific notation, then close parentheses, then divided by, so the divide symbol, and then put open parentheses, type in the second number in scientific notation, then close parentheses. Also, if you don't have a scientific calculator with you right now, you can just Google scientific calculator and it'll pull one up for you that you can use. So go ahead, solve this problem right now and record your work and your answer on your packet. Alright, I'm not going to bore you and talk through the rest of this packet. You're all smart people. I'm very confident that you can figure it out. That does not mean that you don't need to finish it. There are only 3 more math problems that you need to work through. Each one has an example problem in the packet. Complete them before next class. Do not come to class with an incomplete packet. Get it done.